All right, so here we go in section 2B, problem solving with units. So we'll do some more unit analysis to work specifically in problem solving, and we'll look at units of density and concentration. So now that we have some basic understanding of the principles of unit analysis, let's look at solving some problems. Now, we have some steps that might help you in the problem-solving aspect of working with unit analysis. You want to make sure that you identify the units involved in the problem as far as what you're starting with and what you expect the answer, what unit you expect for the answer. And then given those units, you want to find a path or a strategy in going from the initial unit to your desired unit. Keep in mind you can't add or subtract numbers with different units, but you can combine units with multiplication, division, or raising to powers. And then for the third step, when you're done with your calculations, make sure that your answer has the units that you expected. If not, go back and check. Something was done incorrectly. So we did one similar to this in excuse me, section 2A. But let's just, a car travels 25 miles every half hour. Determine its speed in miles per hour. So we're just going to start with 25 miles. And it says every half hour. That's the same thing as per half hour. So it's 25 miles per, how would I write a half hour? I could write 0.5 hours. And the question is, I want this in miles per 1 hour. So what I'm going to do is just divide the 25 by the 0.5. That's going to give me 50. And so I would be traveling 50 miles per hour. You could also just say 50 mph. That's fine. And you may have even figured that out without having to work with all these units, but 25 miles every half hour means you're going 50 miles an hour. Read this next problem, then write a statement about where the student went wrong in their understanding and how you would need to work the problem out correctly. You can pause the video, write your information down, and then play the video back and see if your reasoning is correct. So we see here that the student should have multiplied rather than divide those two values. Okay, let's look a little further. Okay, so we're making pesto. One of my favorite things, by the way. And here's what we know. At the grocery store, it sells for $2.99 for 2/3 of an ounce, and at the farmer's market, we can buy it in bunches at $12 a pound. The question is, which is the better deal? Think of a strategy for comparing those two. There are two ways you could go about this. You could put them both in a price of dollars per ounce or in dollars per pound. You could choose whichever one. I'm actually going to choose the $2.99, and remember the word for is the same thing as per. It's $2.99 per 2/3 of an ounce. I'll take that and change that to dollars per pound. So I've got $2.99, per means divided. 2/3 of an ounce, if you divide 2 by 3, you get 0.666667. So I just rounded that to 0.667 of an ounce. So $2.99 per 0.667 ounces. And I'm going to change ounces to pounds very easily by using the conversion factor that there's 16 ounces in 1 pound. Now, why would I choose to put the 16 ounces on the top and the 1 pound on the bottom? Because I'd like to cancel out ounces and have my answer in dollars per pound so I can compare it with this. All right, so let's do a little math here. So $2.99 times 16, so there's my numerator, 2.99 times 16, and then that result's going to be divided by 0.667. So doing that arithmetic, I get 71.6 0.72, and that's dollars per pound, because those are my units left over. Dollars per pound. So if I purchase at the grocery store the basil that sells for this amount, it's like paying $71.72 per pound, as opposed to the farmer's market, which is $12 per pound. This is eye-opening. And if you can do this, then you can look at prices and make a much better choice. What's interesting is at the grocery store, they will actually have a tag there on the shelf. And in this tag, I think it's in yellow, it'll have the price per ounce. So that tag will have the price per ounce, which will allow you to make a better decision as far as which one costs more, which one costs less, what brand you might want to purchase. All right, so let's look at the next problem. Traveling problem, your destination's 90 miles away. Your fuel gauge shows that your gas tank is a quarter full. Your tank holds 12 gallons of gasoline, and your car averages about 25 miles per gallon. The question is, do you need to stop for gas? So pause the video, think about it, come up with a strategy, and then write what you come up with down, and then compare it with what I get. So here's the strategy I started with. I started with the fact that my gas tank was a quarter full, and the gas tank holds 12 gallons. So if I divide 12 by 4, because it's a fourth full, I get 3 gallons of gas. So I've got 3 gallons of gasoline in my car. Now I know, I looked at the next piece of information, I can get 25 miles per gallon. So I can travel 25 miles per gallon times 3 gallons of gasoline. I will notice that I can cancel some units, gasoline and gasoline. I'm left with how many miles I could travel on 3 gallons of gasoline. So I can travel 75 miles on 3 gallons of gas, which is what I have in the car. So the question is, will I need to stop? What was your answer? My answer is yes, because I'm going to have to travel 90 miles, and that won't get me the 90 miles. I hope you took the time to go back and read the chapter opener for Chapter 2 on global melting. They give you a nice picture of Antarctica and some data about Antarctica, that it is 14 million square kilometers. That's the area. The average thickness of the ice is about 2.15 kilometers. We also know that the Earth's oceans cover a total surface area of about 340 million square kilometers. And when ice melts into water, the resulting water volume is about 5/6 of the original ice volume. So there are some facts about Antarctica. So let's determine what information we need to answer the first question. The first question is, what is the total volume of the ice sheet on Antarctica? And we want that answer in cubic kilometers. So we need to think of volume, and volume is 3 dimensions. They do give us the area. We've got the value of the land area is 14 million square kilometers. So I have a value of area. I also have a value of thickness. So if I multiply the area times the thickness, that would give me my third dimension, which is what I would need to calculate volume. So I've got my 3 values, or actually, if remember, it's length times width times height, but I already have the area. This part of the formula is the area. And that area is 14 million square kilometers. And I'm going to multiply that by the height, or the thickness, which is 2.15 kilometers. Now notice what I'm multiplying. A square kilometer times a kilometer will give me the unit I need as far as cubic kilometers. Now I just need to do a multiplication. Well, that multiplication gives us 30,100,000 cubic kilometers of ice. volume of the ice on Antarctica. Okay, let's look at the second question. Read it and decide what information above you're going to use to answer that question. Well, there's a statement above that says when ice melts into water, the resulting water volume is about 5/6 of the original ice volume. And you've probably seen it with ice. There are air bubbles trapped in it, so it's not 100% solid. So when it melts, it's 5/6 of the original ice volume. Well, if the ice volume is 30,100,000 cubic kilometers, then I would need to figure out 5/6 of that amount to figure out what is the resulting water volume. So I can basically just multiply that number by 5, find that answer, and then divide by 6. Or I could find the answer for 5 divided by 6, and multiply it by the 30 million, whichever way. But the liquid water would represent 25,083,333.33 cubic kilometers. That's how much water the ice would turn into. Okay, let's check out the next one. Suppose all the water from the melted ice flowed into the Earth's oceans. How much would the sea level rise? And we want to state the answer in kilometers, meters, and feet. A little note, if you take the volume of the water, which is in cubic units, and the surface area, that's in square units, if you divide those two values out, the volume of the water by the surface area in square units, you're going to end up with the height that the sea level would rise, and you'll end up with a single unit, because cubic units divided by square units will cancel and leave you with a singular unit, which would tell you how the sea level would rise. So use that as a hint to find that answer. So think about it. Okay, so given that hint, if we take the volume of the water in cubic kilometers, divide that by the surface area in square kilometers, we'll get the height in kilometers. So the volume of the water we found was 25 million earlier. The area was given to us as 340 million kilometers square kilometers. And if we divide that out, we get 0.07377 plano kilometers. So that would be how much height would be introduced into the oceans of the world. Now we want the answer in meters as well as feet. So to take kilometers to meters, I know that there's 1,000 meters in 1 kilometer. I'm able to cancel out my kilometers, and I'm left with meters. So 0.0377 times 1,000 meters gives me meters per kilometer, gives me 74 meters. So the oceans would rise 0.07377 kilometers, or 74 meters, or to convert that to feet, I know that there's 3.28 feet in 1 meter, and if I use my conversion factor here, my meters cancel out, and so 74 times 3.28 gives me an approximate value of 243 feet. So if Antarctica melted and all the ice flowed into the Earth's oceans, the oceans would rise 243 feet. Isn't that interesting?